Welcome everybody. My name is Thomas Trauch and today we are dealing with proposition 9 of Gottfried Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And in proposition 9 he states the relationship between two areas within the semicircle, derived also by the resecting figure, and shows that these areas are equal. And it must be mentioned that in proposition 9 through proposition 12, Leibniz is showing a number of relationships of these areas which he derived by his concept of use of the principle of the infinitesimals, and showing that he can reach the same solutions as the colleagues of his at the time also achieved by conventional methods, in order to show that this concept of using the infinitesimally small areas is actually valid. And let's start for now. First of all, we're going to take a look again at the upper half of our semicircular curve, and we draw out a point at the very center of this semicircular curve, and we draw out also the ordinate, such that we constitute a quarter circle, the upper half of our semicircular curve, which we elaborated on all the time in the previous propositions. And in the next step we are drawing out the segment which is created by the apex point A, the point C3, and the arc of the circular curve. And we also draw out the resecting figure, the construction principle of which we elaborated on in the earlier propositions 6 and 7 and also in 8. And from these propositions we know that the resecting figure then, with the bounds of the ordinate and the axis, constitute an area which we term now the segment figure. And it has been proven in proposition 8 that the area of the segment, here in purple, and the segment figure in green, is that the segment is always half the size of the segment figure, no matter where you place the point and hence the ordinate. And what Leibniz is showing now in this proposition, as some sort of validation of the concept of his use of the infinitesimals, he is proving that the red area, which is now drawn up here as basically the area which is bound by the arc of the quarter circle and the resecting curve, is actually the same as the complementary area of the quarter circle itself. The complementary area being basically the difference between the square of the radius of the circle and the quarter circle itself. Alright, how did he do it? First of all, we know from the previous propositions the relationship between the segment and the segment figure. And this we shall keep in mind. And now we first of all start basically from showing the area of the quarter circle. And from this area we now subtract the area which is the segment figure. And it gives us the very area which is bound by the two curves, the circular curve and the resecting curve. And we keep it in mind. And we know, as I said from proposition 8, that this area is, or we conceive that this area is the difference between the quarter circular figure and the segment figure. In the next step we subtract now the segment or the double segment from the quarter circle. So we subtracted now one segment, so the quarter circle minus the segment is giving us this triangle, But since we know that the segment is half the size of this segment figure, we subtract another segment from the very quarter circle figure, and we subtract it in a way that we just mirror the segment around the line AC3, which is giving us this area. And since we know that this area of the circumscribed rectangle is basically the square of the radius of this quarter circle figure, we know that this is a symmetrical construction. So hence, if we say that we sort of rotate this red area, then we can show that it is actually the same as our complementary area which we stated before. So, and we, by the operation we did, we know that this area is the result of the difference of the quarter circle and the double segment. And again, from proposition 8 we know that the segment figure and the double of the segment is basically the same. We know now that the area of the complementary area of the quarter circle must be equal to the area which is bound by the circular curve and the resecting curve, because it is the case that when you subtract the areas which are quantitatively the same, namely the segment figure and the double segment, from the same area of the quarter circle, you must be getting the same area. So this would be visually very hard to conceive, but by the use of the principles which Leibniz established before in the previous propositions, he made it very obvious that these areas must be equal. And again, the purpose of this was, in my opinion, just to show that by using his concept of the infinitesimals and the relationships he derived from this between the resecting figure and the circular curve, that these concepts lead to the very same solutions which colleagues of his at the time may have achieved by using conventional methods, and therefore demonstrating the validity of his method. And this is just one example where he's showing this. And furthermore, this is not only valid when you use the area of the quarter circle, but the same principle basically applies when you move the ordinate up and down within the range of the quarter circle. So this says that the complementary part of the rectangle, which is bound by the ordinate of the point on the quarter circular curve, and the abscissa, and when you take the complement of this part of the circular figure, then this will always be the same area as the one which is bound by the circular curve and the resecting curve. And just by the use of the principles and the relationships he was establishing in the previous propositions, he made this fact knowable in order to demonstrate that his concept is actually valid. So that was all that was to be shown within proposition 9, and this is going to play out in later propositions as well, as we shall proceed to the next propositions. And I hope you enjoyed it, and stay tuned for the next proposition video coming up. Thank you very much, and bye bye.